Hey guys, this is Mr. Sal. This is a quick lesson on natural logarithms. Which you could probably assume, just based on the name, that they call them natural logs because they occur in nature all over the place. Now, you may not consider that it's happening naturally, but it is. And these things all mean the same thing. So common log, which we've already seen. The natural log means something slightly different, though. So if we have something like a base e of x and a log, right? Log base e of x equals y. We don't have to show that base e. We can make it a natural log. Now I kind of assume that maybe this happened from maybe Spanish, right? I don't know how you would say natural log or natural logarithm in Spanish, but ln, maybe it'd be logarithm natural, because it's backwards in Spanish. I don't know. Not backwards, just different, okay? In any case, it's ln. And if you look closely on your calculator, you should find a button ln. Sometimes it's not capital L. It's, in fact, sometimes neither of them are capitalized. But there's an ln button, which is the natural log button. In some cases, it is possible that you have a log button and then right above it in different colors, like in the ln stuff, which means to get to that, you just got to push the second button and then the log button. And then you'll have your natural logs, which is pretty convenient that these calculators have that. My calculator has both buttons, and it's a capital LN, but yours could be different. The LN stuff is just a different way to write log base e. That's it. Okay. So it says to evaluate this, and as it turns out, we could plug it into the calculator. However, before we do that, again, I just want to look at this, what this would be if it were in actual logarithm form. Okay. So if I change it to logarithm form, it would be log. Since it's a natural log, it's base e of e to the power of negative 80. Now, there are different rules that some people go over at this time. I'm not worried about that right now, okay? What I do want to express, though, on this one, actually, I'm going to use the log one on this, okay? So, on this one, I'm going to say that log base e of e to the power of negative 80 equals y. Again, the only reason I'm doing this is so that I can change this into exponential form, okay? So that gives me my base e to the power of y equals what the log was of, and that was e to the power, maybe it's better to see that in parentheses, e to the power of negative 80. Now we don't need those parentheses because it's not in the log, but we see the bases are the same, so I kind of get to ignore those and we'll look at that later. But y equals negative 80, because if I replace y with negative 80, then I get the same expression, which means the statement is true. So y is negative 80. Now we kind of made up the y business, so the actual answer is just negative 80. Well, how would we do this on a calculator? Well, you'd push your ln button, right? Then you'd find your e button. Sometimes it looks like e to the power of x. At least it does for mine. Actually, on mine, I've got to push the second button. So I'd have to push the second button first. And mine is a TI 30X2S, which sounds far more complicated than it probably should. But I see the EX in yellow for me. It's the LN button again. Second LN will give me that e to the power of x business. And then on my calculator, it gives me the parentheses already, so I'm going to type in, well, the power is negative 80, so negative. That's in parentheses. 80, enter or equals, and it should give me negative 80. This one tells us to evaluate to 4 decimal places, which means automatically that we will have to use a calculator because estimating this one, I don't know how to do it in my head, really. Well, I guess we could change it to exponential form. In any case, so it's the same button sequence on this one, ln. And I've got to push for me, it's the second button. I think some of you guys, it may be like a shift button. And then to get e to the power No, what the heck? It's just the natural log. I apologize. Natural log of 76. Well, then I can push equals. We'll stop right there. We only need 4 decimal places, which is the 7. So I look to the 3. Is it 5 or more? No, it is not. So I keep the 7 the way it is. And that would be my final answer there. Evaluate the 4 decimal places. Same idea on this one. We're just going to punch this into the calculator. So I got my natural log button. And I don't really need the 0. I can just type the decimal. At least for the calculator anyways. 0.55. And then I push my equal button. So once again, we want this to 4 decimal places. So my 4th decimal place is the 4. The next decimal place is a 2, which means that 4 will just stay a 4. Negative 2.9044. All right, this is not a natural log. It's just e. E to the power of negative 8.7. So we got to find our e button, which for me is the shifted form of the ln button. So I've got to push my second button for me. And then I push my ln button. So that takes me right to e to the power of something. So I'm going to tell it it's the power of negative 8.7. Then I can push equals, and it'll give me the answer. Now I have all of what my calculator gave me. However, we only want 4 decimal places, which is the 1. So I look to the right, which is a 6, which is 5 or more. So I got to add 1 to my 4th decimal place, 10 hundredths, thousandths, 10 thousandths. So this would be 0.0002. And again, because of that, we don't consider any of the rest of this stuff. So 2 10 thousandths would be our final answer. All right, there's graphing in this lesson. And whether we know what a natural log graph looks like or not isn't completely important. Now there's 2 ways to do this. We could do this completely as a natural log, or if we wanted to, we could change this into a log. So that would be y equals log base e of x, which would change this into an exponential form of e to the power of y equals x. The truth is, again, the graph is going to look the same either way. It's just we just change the form. So if you like the exponential form stuff, then use that way. If you like the natural log stuff, then use that. All right. But the truth is, we're going to have decimal values one way or the other for the most part. Okay. Now from this exponential form, and I'm going to use a table, and we'll see if we can fit a few values in there. Just from the exponential form, I know if I make a y, the y value 0, anything to the power of 0 is 1, so I get x is 1. So, and we know from the exponential graphs that anything to the power of 0 is 1. It should go through 0, 1. I'm sorry. I put that in the wrong place. 1, 0. Should go through 1, 0 for this one. So I guess it's a little different. All right, whatever. Okay. So the question is, do you guys want to use the natural log stuff or the exponential form? All right, so that means I could ignore this stuff, okay? Even though we have that point, 1, 0. So, I mean, if we said the natural log of 1, we would have gotten 0 anyways. But let's not do that because we've already found that one. Let's choose a different value of x, such as, sure, let's try 2 on this one. So in my calculator, I push the natural log of 2, which is a decimal value. Now that 0.693 is far more accurate than we need to be because on this graph especially, it'd be hard to graph in the hundredths place. But even the tenths place is going to be a little difficult, so I'm going to round that to 0.7. And we can put that in the graph to 0.7, about right there. All right, let's keep going on this thing. So we said 2, right? So let's try 3 then. Try 3. Well, the natural log of 3 in my calculator is 1.0986, so I'm going to round it to 1.1. 3, 1.1. It's not really moving very fast. And maybe it's because of the way I graphed it, but it kind of looks linear as well, which isn't good. Oh, okay, well, let's keep going on this thing. Let's change the x value to 4. Natural log of 4, 1.386, so we'll make that 1.4. 4 and 1.4, yeah, about right there. Well, that kind of makes it definitely not linear. Here's what I want you guys to try in your calculators, because we've encouraged you guys to do this before. But try x is 0 on this to extend my table up right there. Natural log of 0. So that's a domain error, which means that the value is undefined. Just like if we were to try to divide by 0, like 8 divided by 0 on my calculator gives me, well, it says divide by 0 error. But it's undefined. Specifically, in this case, it would be a negative infinity. Now, you may be wondering why that is the case. It's because of this, all right? I'm going to connect these points and just kind of demonstrate what the graph will look like. Now, you don't need 4 points on the homework, but it should look something like this, and we can confirm that with natural log of 10. Natural log of 10, oh man, which is 2.3. 2.3 rounded. And I guess I've kind of hit that a little bit. Well, from this, I mean, there's several things this could do. It could do some funky business like this stuff. I don't know. In actuality, it's kind of that third green one. Since we know that the natural log of 0 is undefined, it means that this line will never touch 0, so I'm going to put a line there. That'll do. So I just put that blue line there to show that our graph will never touch that blue line. So let's try something else then. Let's expand this table even more. What about if I did x is 1/2? Natural log of 1/2 is negative 0.7. So that would be, I don't know, right there. And in actuality, this is just it's gonna get really close to that blue line. Now mine's kind of touching it because of the thickness of the line, but it's never actually gonna touch that line, okay? And the closer to 0 you get, so if I did the natural log of 0.0001, I get negative 9.2. So again, that x value is very close to that blue line, even though it's not actually touching it. So. All right, now this is e to the power of x equals y, which we will graph. So let's make our table, make this one a little bit longer, hopefully a little bit more organized, x and y. And as usual, we'll choose an x value of 0, because anything to the power of 0 is 1. So 0, 1 is right here. All right, well, let's try some other values. Let's try x is 1. So e to the power of 1 is 2.718. So again, I can't graph hundredths or thousandths, so I'm just going to keep tenths, or round it to the tenths. Oh, e, I should have mentioned this earlier. E is called Euler's constant. Euler was kind of like the king nerd of one of those centuries long ago. And he became so good at math that they decided to name this constant after him. And yes, it is a constant value, 2.718281828 and some other stuff, okay? It has some neat values when you get into some engineering and physics and science. But for now, that's all we need to know. Euler, Google him, whatever. He's dead. All right, x, oh, sorry, let me graph that point. 1 and 2.7, about right there. Bam, there we go. E to the power of 2 is 7.4, so 2 and 7.4, about right there. Now we can see from this graph that it's climbing pretty quick right there. And So that helps us to the right, but what about the left? What if I made x negative 1? Well, then I got e to the power of negative 1, which is 0.3678 and some change. We'll make that 0.4. 0.4, about right there. Let's try negative 2. E to the power of negative 2 is 0.13 and some change, so 0.1. Right there. And we can see to the left, it's going to get close to 0, just like the e stuff did, or I'm sorry, the natural log stuff did. Well, let's compare the two, actually. Something like this purple line would be the ln x equals y line. There is a relationship here, by the way. This is what we would call a reflection of one to the other, which means they're kind of like inverses of each other, okay? It's not so important to know, but it's important to see the relationship, I guess, visually for now. Right, kind of like the purple line, for example. That gets really close to 0 but never touches it. So this one, as it gets, or as we move to the negative for the x's on this one, it gets really close to the x-axis, 0, but never actually gets there completely. Now this is a common log, and we should be able to identify the graph on this one, and we can use the calculator to figure out the values for these as well. So let's look at our, and we'll make a table for this. Ourselves a few values, x and y, and we can choose whatever we want on this one. Let's say x is 1, just for the heck of it. Log of 1 is 0, so that gives me this point 1, 0, right there. What about if I did the log of 2? Now this is rounding. Again, I'm just using the calculator on this. 2 and 0.3. Not very much. Let's take this to the extreme and make that a 10. Log of 10, which is 1. Right there. So that gives us this portion of the line. This part. Now because we don't know for now, let's just say we thought, well, what if x was negative 5 on this thing, right? So again, we just plug that into the calculator, and it gives me a domain error, so that's no good. In fact, just from what we did last time, we could try 0 as well, and that should give us another domain error. Yeah, domain error. So what this means, once again, is that this graph is going to get really close to my y-axis, where x is 0, but never actually get there. So let's try a different value, such as x is, I don't know, 1/2. So log of 1/2 is negative 0.3. So we can kind of graph that in here. Negative 0.3, something like this. So again, this line is going to get really close to my y-axis, but never actually reach it. Now, once again, the exponential form with base 10, and we'll pick some values of x. This one won't be as bad. X and y, we'll start with x is 0. Anything to the power of 0 is 1. If x is 1, y is 10. X is 2. 10 to the power of 2 is 100. That's not even going to fit on the graph, but it, I don't know, may help us to visualize that. So let's try some negatives. Negative 1 is 0.1. Negative 2, x is negative 2, is 0. So already when x is negative 2, we see that the y value is extraordinarily close to 0. So let's graph these points then. I got 0, 1, 1, 10. Then again, we can't graph 2, 100. Negative 1.1, still pretty close to 0. And I can't really graph that, so it looks like it's closer to 0. Let's go ahead and graph this line then. Something like this. And then this one goes up really fast. It's not perfect, but it will do.